So I guess we didn't really talk about having like session chairs, but
No, but
yeah.
for this, I'll session chair myself.
No,
if I
you
need
can't
to.
session chair yourself.
Okay.
All right. So our first speaker, we're very happy to have James Wilson from CSU, who is a real outsider to this community. And so we're very glad to have him here to kick us off and tell us some basic and maybe not so basic stuff about tensors. Oh, that was the thing I was going to say. Only that screen shows up in the recording.
Okay, so.
Right. No. So like that will be recorded.
I see.
And the camera.
And the camera.
Like, if you try and do stuff with this screen.
I see. That doesn't work. Okay, right. So if I go to .cam, I should use this one.
Right. Yeah.
I can't tell if you're hearing me just because I'm talking or because it's through the microphone. But
I don't think there are speakers in here.
Okay, then that's fine. So the mic is just for the recording, so then we must be okay. So, all right, let's get started. I think some of you probably were reading before I came in, but if you want, I've put together numerous slides. The goal of it is actually to have more slides than anyone could ever give in a talk, because you should not expect that I know what I'm talking about. So what I kept doing was learning a little pocket again, and then when I learned about that pocket, I'd add it to my slides so I'd never forget again. My intention is for you to explore it on your own. These are just notes. They're not complete. They have some hints of where to go, and I hope to expand on them over time. So if you write down this website, you'll see that maybe I'll update and add references to it and so forth. My goal is to just make a compendium of things that I found useful when doing research on this. And I would like to keep this at the level of people who have maybe heard the word tensor from some category in their life, but they aren't necessarily wanting to answer the questions of what it is. So if you're a super expert and you can tell I'm doing it wrong, I don't mind being told, but think of the rest of the audience and make sure that you're not just sort of proving that you know more. So here's the people I want to give credit to in this particular version of the talk. We'll have more to say in later in the week, but these three people have contributed to some of the mathematics I will describe here, and also the funding agencies that have been responsible for this research as well as this conference are listed there too, and we're very grateful to that support. I don't want to linger too much, but I do want to say a few things that are going to happen. You have to pick a lane, and we have multiple people in different disciplines, and there's no way to find the satisfactory choice for everybody. So I made a choice that made me happy, and you're stuck with it. So in particular, a common thing I'm going to do is abbreviate a list of numbers in sequences, just bracket around the A. That's just a shorthand notation. And I'm going to try to refrain from set theory notation, in part because it actually falls short in a couple key theorems, so that's the real reason. But if I was to give you the fake reason, it's because, well, we have people who might be more comfortable with writing an algorithm. And there really aren't sets in a program, there's just sort of data structures. You just say an integer is, 8 slots that you can put a 0 or 1 in. And that's different from, say, what a mathematician would call the set of all integers. So to keep that sort of honesty there, I'll use this notation from type theory of a colon instead of an element in. It will have a very specific role in 1 or 2 slides. I may not even tell you where, but I wanted to be honest with it. But the more important ones is going to be function notation. One of the things that happens with tensors is that we interpret them sometimes as data, just grids of numbers, and sometimes as functions, moving vectors around, and sometimes as functions of functions, and it gets very confusing after a while to know what you're trying to say. So let's do a little bit of translation. If I'm thinking about a list, a grid of numbers, then I just need to give you indices. Maybe in this case a 2D grid. So I'd have a range of numbers A and a range of numbers B, and f of AB is just looking up that coordinate. That's the standard kind of a matrix row column. Whereas here, what I'm trying to think of is the very same data, but I'm going to incorporate into this the idea of it being a function. That if you ever give me an input A, then later on you could give me a B and it would come into a C. So it sort of give me the first index, which row you're talking about. Now I have that entire row as an index. And often, just because we all get lazy, you start dropping these parentheses of how we nest them. And this is a real problem for mathematicians who spent a long time learning about sequences, exact sequences. Also use this for composition of functions. I'm just indicating that the notations can get blurry. Just ask. If you feel confused, then it's possible that I accidentally used a notation without intending to confuse you. No matter which background you come from, somebody's notation means something else there. And then the last kind of notation is you might think of these as ordered pairs, A, B, that evaluate to C. And that's a perfectly equal notation for what's going on. All right. If you want to explore more at any point in the talk, you can take the slides and explore more. You can notice that there's information that is, whoops, you can go down and see some more details as to why I'm doing certain things, what type theory really is about. That's for you to explore on your own. But if at some point you'd really like to see what I said or linger on a slide because you didn't know what I said, you can move around your own smartphone your own way. Things that I decided not to put in here, partly because I felt there was really good expositions elsewhere. I'm not going to go into Tucker decompositions. This is a very, very active area of tensor theory, how to decompose a tensor and get smaller dimensional representations of the same information. Tucker decompositions show up everywhere in engineering circles for this task. I think there are equivalent tools in other contexts. That's one of the reasons I'm not featuring it, but mostly it's because a lot's been written on it, and I would only be just repeating what I've learned from other people. And likewise, SVDs, which is rather related. I'm not going to emphasize that, though there's actually several places where that's actually happening in the background. I won't linger there. And then later I'm going to talk about things like data structures and categories. The sorts of things that, say, make this mathematically interesting to me, but not to try to make you mathematicians, but if you are a mathematician, how you can serve your community of other scientists. And if you're interested in sort of engineering challenges, you probably will see that even though you don't care about categories, the questions that get asked turned out to be questions you were asking too. So we'll see what this is. All right, this is the main slide of this entire talk. It's to give us some sense of what we mean when we all speak of the word tensor. And it is surprising to me how many pocket communities of this word there are. And so at one point I decided to see, could I put all the types that I was aware of at the time into a slide? It got very crowded, and then since then I keep finding more, and I can't put more on this picture. So I'm just going to repeat this thinned out picture of the world of tensors. In particular, someday I hope that things like Wikipedia will bother to put in the multiple interpretations. Right now when you go, you get one very narrow slice of tensors, and I think it's rather under-informative. So let's take a few of these and see where this comes from. Perhaps the oldest, the word tensor shows up in work of Hamilton in his Elements of Quaternions. He was fascinated with his quaternions, a great invention, I'm sure, but he was limited by them too, because he only saw things as three-dimensional. He wanted his ijk to be the real numbers, and so when you take an ijk vector, one of the things you learn is that you could sort of think of an ijk vector of length 1 as being on a unit sphere, right? It's pointing somewhere, so it's got some angle up and some angle over. If I start multiplying these quaternions, one of the things you learn is that they rotate to vectors. So to rotate, he looked up some Latin words, and he found versor was the word he liked for like same word as reverse, that same root word. So he had these notions of versors, which were length 1 quaternion numbers. But of course, you have quaternions that don't have length 1. So what should you do then? Well, okay, geometrically then, you have something that's pointing out in space, and it's longer or shorter than length 1. So when you multiply, it'll rotate, and then it'll apply a tension to stretch or shrink. That was his idea, and so he called those things tensors. Or actually, he called the length of them the tensors, and you would scale by the tensor. And what happened is that, in this book, he introduced so many wonderful words that you all know. The proof that it's influential is the word vector, introduced in that same book as axioms. The same axioms of a vector space that you teach your students or that you use yourself, they're in this book. So it's clearly an influential book. And in there he says, okay, length of a quaternion will be a tensor. And so all the people who had mechanics worked out with changing rotations and stretching things, or curvature, something was flat and you applied a tension to curve it. All of a sudden, all of those started having the word tensor attached to them. And over time, as it turned out that you couldn't just write that with just the length, you might need a grid of numbers like a stress tensor or something like that, then those notions of tensor overtook the notion of length, and it just became anything that related to how you bend or fold something. So geometry in the Ricci-Levashivita convention was what's sometimes called index calculus, a way of writing down curvature equations, things about how shape is bent, and a lot of them got called tensors just out of respect to that origin. And by then it was basically grids of numbers. And immediately it was used in the sciences because, after all, any kind of mechanical system undergoes tension and rotation, so it was very natural to transport the language. So in kinematics you had things like stress tensors. If you try to deform a surface by applying something on it, it doesn't just go in the direction of your motion, right? Because there's some kind of material strength to it. It might apply some tension in one direction and another. So you write down all those forces in a grid, And you have to record that as some multiple parameter system, and that became a notion of a tensor in a kinematic type thing. The most exciting, of course, occurred in the Copenhagen Convention, settling out what was happening inside of quantum mechanics. And one of the interpretations was, let's model all the states of matter as dimensions of a vector space, all the possible states. And then as you transition from one to another, it's a basis change. Technically, there's things like unitary and Hermitian operators, observables. We have later people who are going to give us better talks on that. But the idea is you start to model your systems with these complex vector spaces having some high dimension, and when you bring them together to make new systems, then how do you bring them together? Well, there's two natural choices. You could just direct sum them together, add the dimensions, or you could take their tensor product. You could just glue together and blow up the dimensions by the quadratic, or by the product. And the right answer turns out to be to take the tensor product. And then what it does then, if you do this, is that you see examples of things that you might write with this perhaps goofy notation if you've not seen it before, but this Dirac-Baraket notation is trying to say that, well, some states of matter don't decompose naturally into just what happened on the x-axis and the y-axis. They're sort of an entangled component of both types. And there are better ways to explain that, but that's not my goal today. Sometime in around, I think it was 1938, all of this sophisticated machinery was looking a bit sloppy to the mathematicians. And Whitney, there's a wonderful book out by the AMS recently on the life of Whitney, and he was just one of these guys that just loved learning and exploring different kinds of mathematics. He was really well known in geometry and topology, but also did a lot in logic and algebra. And at some point, he just didn't like the notion of tensors being so vague. You know, if you look at the books at the time, tensor is defined as an object that is invariant under the change of frames. You know, this is the definition. I'm not sure what to do with it. And he didn't like it, and I can understand why. So he introduced what we now think of as the tensor product. If you're an algebraist, you were probably not even aware of a tensor. You learned the tensor product, and you learned things like universal mapping property. This is the person who did it. And he did it really well. He did it in great generality because he was already seeing the hints that there was going to be this invention called category theory about 2 years later. So he's sort of playing in that direction, and he puts it out there with a universal property and the things that you now know, including the notation. And it led all the algebraists to jump in and start talking about tensors. But they did it only through his lens, in that everything to them, they didn't care about the elements in the set. They cared about the modules being glued together and making bigger and bigger free structures. And that has had a strong, lasting, perhaps negative influence on the subject. We'll see. Late to the game, but certainly not irrelevant, has been the birth of data science, aggregation of data at a level we've never seen before. And you put it into tables, right? You know, I collect my student grades and I put them in a table. Do I get to call that a tensor? Well, there's reasons you can and reasons you can't, but let's say that's the first thing you do. To be something tensor related, from my point of view, you have to keep linear algebra at least in the background. So let's think, what's a fair task that if I collect the grades of my students would apply a linear algebra application to the data? Average the scores. All right, when you average the scores, what are you doing? You're taking every row, every student, you're putting a weight on each of the homework assignments, you're multiplying it by that weight, and you're adding them up, which is just a dot product. It's just a linear transformation, right? You're applying some weighted vector to it's a contraction, a tensor contraction if you want that word. Very natural thing to do to data is to add up the rows of something, add up the columns of something, weight them, do this in many dimensions. And as soon as you start playing with that, you realize actually it is fair that whenever you collect data like this, that you'll explore it with some linear algebra. And that's when you're really headed down the tensor landscape. But what we were not prepared for, I don't think anybody really planned for this, was the scale. Not just in terms of total volume of numbers, but the dimensionality. Like, we were used to things like a Cauchy stress tensor being a grid because you could see the XY coordinates, or XYZ if you were really stressed. But none of us took determinants beyond 3 by 3 matrices. So now you take these ideas and you plot them on these 1,000 by 1,000 by 1,000 by 1,000 24-dimensional systems, and you realize we did not design for this level of sophistication. And that's what's leading to a certain amount of interest today. Well, what are the goals? You can't summarize everyone's goal from a subject area that's 100 years more old, but here are some things that I see emerging. Look at linear algebra as a guide. Linear algebra is remarkably successful in both applied and pure mathematics and in physics and engineering and computer science. So maybe there's ideas there that you should harvest. So what are the things you do when you have linear algebra? Well, you ask questions like this. You give yourself a matrix T, which I'm now going to think of as a metaphor for a tensor, and you ask, can I change the basis on the rows and the columns independently to get something simpler to look at? Maybe it's just sparser information to store. Maybe it's actually telling me an invariant that doesn't care about a basis. Well, that would give you the rank of this matrix. So let's put our thinking caps on and come up with a notion of rank of a tensor. People have done that. Are you speaking on that?
A little bit.
Okay, so I won't say more, but there is such a thing. Same thing with other types of transformations. Maybe I want to keep some symmetry alive. I might have some non-degenerate inner product, but it might have a signature, right? It might have some kind of spatial coordinates and then some time coordinate. So positives and negatives. Is that well defined? Or is that just your choice of coordinates? Well, it can be well defined. That's something called Sylvester's theorem. Well, okay, so now let's take that to three-dimensional grids. Is there such a notion? Is it well defined? Is it well posed? All these great questions. What about Jordan normal form? I want to find out how a transformation where I change the rows and columns by the same transformation, or I guess the inverse, right? If I conjugate a matrix, what are the various things that are kept the same? Eigenvalues, for sure. Well, is there such a notion as an eigenvalue for a grid of numbers? And people have done this. You can explore my version of what these things are. I'm not going to go into them except to say these words are showing up. Yes, they exist. No, they're not what you think. They're not so easy, okay? And so over the next week, I want you to explore why that might be the case. Ask the people who've been thinking about these questions, what are the hard questions about? Why is it that linear algebra fails to generalize so well? Because that's where a lot of really interesting mathematics and computer science is happening. There's wildness. P versus NP might be solved this way. I'm not getting into it. I'm just telling you, explore the slides and then ask people. But let's not be a joke about this. I know that it's great. You know, you're writing your next grant proposal. You want to get funded, so you put in, we're working on quantum something, or we're working on big data. You put in all the buzzwords. Don't make it a joke in your own research. If you're not doing tensors, that's fine. You're doing something. Explore what you're exploring. But don't just go back to your giant filing cabinet and call it a 5 tensor, right? This is my best picture at a 5 tensor. I thought, how do you draw this? So if you have a bunch of tables inside there, those would be 2 tensors, right? They have rows and columns, and then you could have a drawer, which is rows, columns, and depth, and then you could have a front face, and then you could have a library. So this was my imagination of high-dimensional tensors. You can have your own, but it led me to try my hand at an XKCDC slide. So, okay. So those are the examples that I'm bringing to the table. There's plenty more beyond that. I'm not trying to limit. In fact, what I have is one of my slides, and one of the discussions I'd like to have this week is if you're coming from an area where you feel that my slides and my interpretation are underrepresenting your view of tensors, I'd really like to know that. Because I'd like to get a better handle on what theory is missing, explore it a little bit better. And if you don't see that there's a hole, but you just think that there's something to explore that would add to this, same thing. So tensor spaces, this is my view of what a tensor really is in a way that sort of goes a little bit beyond what Whitney did. There's a reason why Whitney did it his way, but that was 80 years ago now, and there's some updates that I think are important to have. So unfortunately, maybe I could have done this with less notation, but I didn't. Maybe that's the right answer to give you. So I'm just going to go through my notation. You're probably familiar with this symbol because of the tensor product in the sense of Whitney. This symbol, I want you to think of as just division. But what's the thing being divided? It's similar to Whitney in that we're taking abelian groups or vector spaces. We'll just say vector spaces, but everything I'm saying can be done on the level of modules. No concerns about torsion and stuff like that. And so if you look at the top line, this here, this is just saying all these sort of linear maps. I guess I only care about the addition, that so long as it's distributive over the addition, that's good enough for my purposes. But you can put scalars in there if that's important to your life. And along with this fancy set, which you might call HOM, but at least this is more compact and it serves a better purpose later on, you also have an evaluation of these functions, right, to stick this in. And that evaluation, if you stop to think about it, is distributive both on the left and on the right. What do I mean? Well, here by definition I said if you add the 2 vectors it distributes, but if I had an f plus a g, then I could distribute on that side too. So it turns out this is also a bilinear system, if you know what that word means. And so it means that this will actually induce a tensor product, and I claim it'll be the same space there, which is why I'm calling this division. It's like I'm canceling the denominator. There's a later slide that'll make this a little bit more apparent. If you like category theory, what I'm slicing in here is a completely universal product type definition of HOMS that has no category in the background. It's just building it directly. You can scroll down and explore that. All right, but given that, you don't want to just think with just one linear map, a set of linear maps. So this is just a set of linear maps from V1 to V0 if you like. That's a good model for it. So maybe I want to think of more than just one. So again, I'm going to be lazy. Instead of putting parentheses around everything, I'll think of fractions A over B over C as being normed to the top, right? The very first ones get the parentheses. You just keep adding to this. So if I add one more layer, then everything that's in here is a function that takes a V2 and turns it into a function from V1 to V0. Which again, remember, we might not always write these parentheses. And so if you unpack that notation, we'll do a little practice here. You could take a V2 and then a V1 and plug them in this order and you'll get something in V0. And if you stand back, you'd think, well, that's also the same as a pair of values going in. And this goes to that first notational slide. Lots of ways to describe a grid. You can give me the row and then the column and then your depth and keep going down the list, or you can give them to me all as a big tuple and I shove them in. You could give them to me in the middle and then I go look up the new ones at the end. There's lots of orders, but all of them are trying to indicate the same type of idea. So let's see if we can figure this out with some notation, or with some examples. So let's take a standard 2x3 matrix over real numbers. No reason to be cute here. So here's one way to interpret what's going on. I'm going to use this notation of this half bracket, which we'll call bra in the Dirac convention. And I'm going to say, suppose that I have one of these things, and it's just a function from R3 into R2. That's what this interpretation is telling us to read it as. So it's just starting from R3 and ending in R2. So how would I actually think of implementing this? Well, don't overthink it. The whole point is for this to be somewhat natural. If I take a vector that's an R3 vector, I multiply it by my matrix. That's the definition of this function. But there's a different interpretation entirely. Right? If I give you a 2x3 matrix, who said you had to have a column vector? I could have had a row vector, an R2 row vector could have been fed in to spit out an R3. How do I indicate the difference? I have to do it either in words around there, or I might, in this case, I'm using notation. So the swap here is, I've swapped these two roles to indicate to you that I'm using it now in the row perspective rather than the column. Same matrix, but it has a different interpretation. This gets at something fundamental. When someone tells you that a matrix is a tensor, that's incomplete information. Because you don't know how they want to use it as a tensor. Is it a function from R2 to R3, R3 to R2, or could it even be something else? Could it be that they want to use rows and columns and come up with a single constant? Or something even more. Like the point is, a tensor is not just the grid of numbers. That's the same as putting that little joke, oh, I call my filing system a tensor. If you're not using the interpretation into some linear system, you're failing to use that linear algebra aspect of a tensor. So here we see that I actually think of this as a repeated function. It eats things from R3, they become functions from R2 to R, and together you get a function which we might call a bilinear form. Okay, these are just possible interpretations. And that's how I would denote it. Well, all right, so there's typos in the slides, I apologize. But so this one would make sense if I was thinking of it as R3 to R2 to R in the curried form if you're a computer scientist. And if you put it this way, then what I meant to have was a comma there. So it'd just be a pair, an ordered pair fed in. Same interpretation, but just different thinking of the function. Whether there's two domains or one domain, same function overall. If you can do it with 2, you can do it with n by induction, right? Of course, all those claims have to be supported, but yeah, the basic thing is I can think of this as a function that eats a VL and then it eats a VL minus 1 and a VL minus 2 all the way down until it's done, or it just eats them all at once. This is your call. And I'll write that by saying it's something of this type. This would be a perfectly good place to have a question. I don't need it, but if you feel like, boy, that didn't settle well. Yeah.
Actually, I have a question about the previous slide. So normally, when I would think of Dirac notation, I would think of the difference between the first two as like I should turn M into a ket.
The difference, yeah, you want to act on the other side. Yeah, I mean, honestly, of course, whether something's bra or ket is a duality, right? There's some kind of op going on there, and I'm trying not to have an op. I'm just trying to have a different interpretation.
I see.
So like, who?
The duality there.
Well, it's that there isn't always a dual, like that. That's the reason. So, but you're absolutely right. In many situations, you then add some dagger to the category, which allows you to swap sides, and then bras can become kets. But that's assuming there's only one possible interpretation. When I have three things, there's an S3 shuffle, and I feel like it's insufficient to just have the bra becoming the ket. Then you have to like rotate the bra or something. I don't know, but it gets a little silly to go too far with it. So you're totally right. That's a very common convention. But I didn't opt for that here. This won't satisfy all the uses. This is just one interpretation that I think works pretty well, but it won't cover everything. Thank you, Josh. So this is my definition, and I really would welcome discussion. Perhaps let's not take away too much from the talk if it's silly, but I don't mind being taken to the bar and told this is the wrong way to think of tensors. And then I'll absorb what you're saying, and I'll come back and repeat some merger of these two and take all your credit. So, but yeah, so this is my interpretation. Something is a tensor if it's an element of a tensor space. That's my solution to arguing with everybody about what a tensor is. A tensor is an element of a tensor space, just like a vector is an element of a vector space. Don't have to decide on what interpretation you have. Is it a grid of numbers? Is it some differential forms? I don't care. It's an element of a tensor space, therefore it's a tensor. Just like a vector is an element of vector space, that gets to be called a vector, right? That's my definition. Now we can argue about whether the tensor space is properly defined, and that has such weak history that that's a good place to make the adjustments and nobody gets hurt, right? Tensors, you're going to have knife fights. That's not a tensor. Yes, it is. But tensor space, no one's going to get hurt if we have to change the definition. But here's my attempt at the right definition. You give me a list of vector spaces. Let's give those names. Let's call these the axes, and together they make the frame or the reference frame. So a reference frame might be a grid like this. Then you'd have an axis here and an axis there. And what's the total number of columns? That's the dimension of the vector space for that axis. What's the total number of rows? The dimension of the vector space for this axis. Together you get something that frames a matrix. That's my interpretation. So if you had V0, V1, that would be a matrix. V0, V1, V2, that would be a list of matrices, or a three-dimensional grid. 4 of them, 5 of them, you get filing cabinets, rows of filing cabinets, libraries. Use your imagination. So, and then just to have some vocabulary, some of this is sort of, I used a lot of previous texts by Malsev, Selinikov, J.M. Landsberg, various textbooks that have the words tensor pasted all over them. And they all use different words, so I can't confirm these are the right ones, but these do seem to show up often enough, and they do avoid certain problems. Like the word rank is well overused, so be careful using that. Dimension can be very confusing because you could be thinking of a dimension of a three-dimensional box, but then there's dimensions as in the dimension of the vector space of this axis. So for those reasons, I'm selecting these words. Valence will be the number of vector spaces you have, rather than dimension. Even if you think of it as a three-dimensional box in your head, I'll call it a valence 3 tensor. And the dimensions will be reserved for the axes, the actual vector spaces that frame the boxes. That's my vocabulary. It does solve some problems. If you don't like tensor spaces, I'm sorry. But you're stuck with them because it turns out every tensor, by any other definition, turns out to be a tensor space. If you give me one grid of numbers, just one, you only cared about one tensor in your whole life, the Netflix tensor. You're going to make we're probably not going to make any money, it's over now. But when you were trying to make money off the Netflix prize, you were given one tensor, and that was the only tensor in your life. Why do I claim you had a tensor space there? Well, because you could have sliced it up. And take every one of those slices and take the span of them. That turns out to be a tensor space, but on one less valence. Because you sliced along one of the axes, so you remove that axis from the context, but you still have all the other axes. So even if you don't like the version of a tensor space, it's actually in the background of every tensor. And likewise, if you have a tensor space, but you prefer the study of a single tensor, you can then glue them all together and make that into one tensor in a valence higher up. So your valence is kind of a little elevator between spaces and tensors. And you can think of nothing more than just a matrix to see what I'm saying. I give you a matrix. What's the associated space? Take the slices of the columns, take the span, the column span. That's a vector space. It's a subspace of something, and that's the associated space. But if I give you a space, I can glue together a basis into a matrix, and now I have a single matrix. Totally interchangeable concepts, and it gives you a pretty good sense for what the difference is between a tensor and a tensor space. And this is what I'd like to make sure, I think I've hit this over the head well enough. I am happy to be told that there's deficiencies with these definitions, just as long as you're polite enough to explain them to me. Okay. All right, this is one of the slides that I don't want to linger on, but I do want to sort of put it out there. The reason to use colons instead of the element of symbol, the reason to use type theory instead of set theory. I'm very much interested in the computational value of tensors. I think that's one of the strongest places people have put energy and time into, is how do we make tensors into something we can compute with, get information in and out of machines. And when you do that, one way to study computation is to ask the questions about where they are in terms of difficulty. How do they compare to other hard or easy problems? And if you think back to this definition of a tensor space, this is coordinate free. It just says, give me some vector spaces and give me a representation into functions. This is really what we would call in the computer science community a black box model. I don't actually have to know how the tensors are described. Maybe they're a bunch of sparse matrices. Maybe they're lists of lists of lists. I don't know. But whatever they are is irrelevant to this model. It's a black box model. I can do all the arithmetic I want on this model. And so you can ask questions in black box algebra. And if you ask questions, you can start to ask, well, is this in P, NP, various things like that. The trouble is, in black box algebra, you make assumptions that you have arithmetic rules, ways to add and multiply and so forth, but you have to also assume they have axioms, like that the multiplication is associative and distributive and stuff like that. In many of the original models of black box, none of that was given. It was just assumed that, well, you wouldn't have asked a stupid question. I have seen enough programs to know that's not true. So there is a gap between existing black box models and actual P versus NP. You can spoof a black box model with something that isn't actually one of the things in your category because it doesn't satisfy the axioms. And so if you're writing theory of black box algebra in the standard sort of 1980s model Babai-Simoretti, then you're talking about something specialized called the promise hierarchy, which means that you're not going to prove things about P versus NP in separation without doing a little bit more. And I'm not sure what's qualified as a little bit more, but I'll give you something that's sufficient. So there may be something even weaker than what we do, but Heiko Dietrich and I puzzled on this, and particularly in the category of groups, but it applies more generally. You can make this all fit the standard decision hierarchy by imposing the condition that your data also give proofs of the axioms. And to do that, you need something robust enough, and type theory is robust enough to do that. And it wasn't possible back in the 70s and 80s because there wasn't, at the time, even a way to talk about polynomial time with types. It just didn't exist. But a recent breakthrough in the programming language community by Acatoli and Dalago has made that actually punctuated as correct. We can actually write normal forms and produce reliable polynomial time reductions. So now we can actually do decision hierarchy. We can really talk about P versus NP with tensors. Instead of the wink and nod, well, as long as you promise it's a tensor, which might actually have hidden all the computational complexity. So that's just, the purist in me wants to study that more than, you know, Netflix tensors. So that's an aside. If you don't care about complexity, you can now tune back in. All right. This is more of a little playground I want you to explore as you wish. I'm just going to point out that once you think of the metaphor of a grid of numbers, it's really hard not to do something from this list. You have a box, you put it in front of a child, and they will topple it. And you should do it too. We give these all kinds of names, but the idea is really just that. You stack up a grid, and you can tip it forward, you tip it this way, you know, and depending on what your valence is, you can have all kinds of permutations available to you, rotate, shift around. I want to make a key point that is often misunderstood. Is this a generalization of the word transpose? So certainly if I have a grid, and I do this to it, that's a flip, that's a transpose. And if you look in the linear algebra textbooks, you see that transpose needs to be very carefully thought out because it's the same as a function from V to the dual space and it's coordinate based and so forth. Notice that what I wrote on the slide has no coordinates. A shuffle of a tensor space is actually a functor. It is not a coordinate system. It is not a generalization of a transpose. Now, I'm not going to go into detail because I need to tell you what categories are in this context, so in the lecture later in the week, I will go into this a little bit more. But I'm just mentioning there is a small difference in the conversation that really matters when it gets down to making algorithms. And the last thing I want to say is this is just for historic. I am amazed at how many people have invented this. All on their own. It's an obvious thing to do. Like I said, you put boxes in front of a child, they'll topple them. But maybe as a professional researcher, you should Google, has anyone done this before? And the answer seems to go back at least to Ricci and Levashivita. I mean, lowering and raising a tensor's index is exactly this. So yes, it's a valuable tool, use it, and if you found it on your own, feel pride, but it's like rediscovering, I don't know. Yeah, you didn't discover it yourself. Oh, you're not the first there. All right, I feel like this disclaimer is appropriate. I'm going to use a few shortcuts throughout the talk and in my life to make life easier. It's easier to just write all your indices to go to 0 because it's one of the numbers out of my list. So I can always shuffle things to make 0 be the outcome that I'm looking for. And I may not tell you that I shuffled it, but you can understand that if you wanted to actually look at the axis 3, you could shuffle 3 to 0 and recover roughly the same thing. Anyway, if you get lost in the notation or this is, you were told. By not leaving now, you've agreed to the confusion that's going to ensue. Another way to build tensors is really common is to stack them up. Right? I just take a bunch of boxes, I stack them up. Again, this is actually a functor. This is not some kind of coordinate-based system, and this is just displaying that you could do this in a coordinate-free way. Mostly just to emphasize that if you stop to think about what these things are doing, you will force yourself to study questions like what categories are involved here. Is this a categorical coproduct, a product? What's really going on? And that sophistication leads to some interesting answers. The reason I want to bring this slide up more than the others is this is a common way to have encountered, at least in the algebraic settings. I'm not so sure in other disciplines, but within mathematics, systems of forms have dominated the study, I think, since people like Kronecker. They've been studying this. So I don't know when Kronecker was around, but that's 100 and something years. So list of matrices. I give you a list of matrices. In what way is this a tensor? Well, you can see all the formality here, but if you just want to think of matrices, you can just think I have a bunch of matrices like this, and I glued them, whatever shape, face I was gluing them together, and they make a three-dimensional thing. That's a tensor, we've agreed. But this is often how we see it. And another way that's a little bit more sophisticated and can really throw you when you first start seeing these is that many people don't actually even want a matrix anymore. They talk about something like a quadratic form or a cubic form or something like this. And it's just a polynomial in homogeneous variables, right? So homogeneous just means that the same number of variables in each term, indeterminate. So here's an x squared and here's an xj, jk. That kind of system does not look immediately like a tensor, but I claim it is because what we're hiding in our heads is to do this polarization to get the corresponding bilinear system and then glue them together into a big tensor. So don't be surprised when you're reading a number theory text and all of a sudden there's a tensor that you didn't see coming. It's probably something as generic as this. There'll be exceptions, but it's really not meant to be that these are that different of a topic. It's just that over time we found that we could change the notation and we like our favorites and we approach it through different toolboxes. Slices, I've already talked about it. You have a box, you can slice it up. It kind of undoes a stack. The tensor product and me learning how to do GIFs. So this is mostly an excitement to the community of tech users that I was able to make PGF do this. And that's all I have to say on this slide is look at the pretty colors. No, I do have a slightly better point. When you see in an algebra textbook the definition of a tensor product, there's a pedagogical goal more so than a definition of a tensor product. The pedagogical goal is to explore things like universal mapping properties. How do you get them? Well, from the universal property of freeness and so forth. There's a different goal than making it the simplest definition of a tensor product. So I would like to cut through all that and just tell you that a tensor product is just to take rows and columns and make a grid. That's it. Now you might say, oh, but that assumes the thing was free and it doesn't have relations. Oh, come on. Knock it off. If you have something like that, then your module that has torsion is just a relation of some free thing divided by some kernel. And you write this, and you write this, you multiply your matrices this way, and then you write down the ideal of the product, and that's the quotient. There's no universal property nonsense here. There's no free thing on this infinite abelian group that you cut down by a zillion relations you can never handle. In particular, I'm emphasizing this, if you ever are building software, and you take the textbook definition, you will die. You will not build a tensor product. But this you can build because it's a matrix. It's a matrix, and it's quotiented by a subspace. Very computable. If you don't know what an ideal is, this is a wonderful little nugget. I don't know why this isn't taught. Maybe it's not known. I don't know. But it's a pretty straightforward thing to verify. Give yourself any distributive product between three abelian groups. Now, normally you'd think of a ring, so you'd have the same letters, A. But I claim every proof you have never used the fact that they were the same letter. To think of something being a substructure means that it's closed under the addition. That I'm hiding by this less than or equal to sign. It's closed under the addition. And then I need to close it under products. But if I look at this, X is under U, Y is under V. So the product only goes into W. So I only need to make a substructure that X times Y is contained in Z. That's all I really needed. That's what makes it a sub-ring, a sub-module, a sub-any kind of distributed product. But then, what are the ones you can quotient by? In algebra, you can quotient rings by ideals. And you had to check that in order for these cosets to have some well-definedness principle, they had to absorb on the left and absorb on the right. And that's it. Nobody said they had to be the same letter. And I claim that the exact same proof proves that you can take quotients by any distributive product, provided that you absorb products on the left and products on the right. And that's what this picture is doing. I'm saying throw in all the products on the left and all the products on the right so that you definitely absorb and you are an ideal, therefore you can take the quotient. All I'm saying is don't make tensor products harder than they have to be. It's great if you have a pedagogical goal, and I'm not taking that away. But if you're just trying to get people to understand a tensor, don't lose the matrix. It's pretty straightforward. You know, you can teach this to undergraduates. This is a tensor product. Make the grid, okay? All right, if you follow all this stuff, this is just to also emphasize there are some low entry points that we sometimes hide. Normally we don't use this /O notation, right? Or this kind of O/ notation. We would use what instead? Let's remember what it was. It was functions from B to A that were linear. We'd call it HOM. Write all of these equations with HOM. I mean, you'd die and you wouldn't know why you were writing them. But you write them with this and you realize I'm just saying take the fraction A over B, multiply by B, you're left with A. Take A and multiply it by K. K is going to play the role of 1. It's just A. Multiplication is, let's take this. This one here. A divided by, I like this one. A divided by B divided by C divided by D. That's a fraction of fractions. You invert and multiply. Oh yeah, look, we invert and multiplied. It's incredibly memorable, but you put HOM in there and you have no idea if this is true or false, and you will spend an hour of your day confirming something totally trivial. So I'm just recommending that sometimes the algebraist may not have helped you. There is a great reason to use HOM. I'm a category theorist in some sense. There's not anything wrong with HOM, but this might not be the right place to use it. Last sort of general bulk thing here I want to describe. Contractions. This is, again, exploring with TIC-Z. This is adding up all the coefficients in a grid along some axis. Maybe you weight them, like weight my student grades, homeworks are worth less, they're worthless, and the exams are worth more. It's a nice little joke. It worked. I'm going to do one contraction that I like, mostly because I wanted to see if I could do this. When I was a child, I was working with BASIC, and I tried to make my own graphics thing in BASIC. You can't do it. But if you try, then you will explore these sort of things you might do, like rotating images or sort of trying to find shapes and stuff. And so I knew of this sort of thing without really understanding the mathematics, and I never got it working. So then I thought I should try this again sometime in my life. So I'm going to do something called tensor contraction, but I'm going to do it specifically for convolution. So let me zoom ahead here. Suppose that I have an image. Probably it's much more sophisticated than the one I typed into my computer algebra system, but this I could type, and I wasn't about to like make a little read the JPEG in and turn it into numbers. But yet in real life, there are software systems that snorkel in the image and turn them into numbers for you, and then you can see it as a grid of 1024 by whatever number, and each little pixel is a number that's the right kind of gradation, grayscale, color, whatever. And then your job is to understand what's in this image. And the first thing is, do not think of it as a matrix. There's no linear algebra in the photograph of a kitten. That's not the thing you're trying to do. Just think of it as one big flat matrix, or one big flat vector of length equal to the dimensions, 640 by 480. Whatever that number is, that giant long vector is the way I'm going to think about it. But I do want to keep the sense of shape in there somehow. So what do I do? Well, there's lots of theory that's gone in, 30 years of research or more, hundreds of years of research maybe. You take a little plaquette, let's say a 3 by 3 grid around each pixel. That little 3 by 3 grid is telling me who's a neighbor of this pixel. And so for example, let's take the simple task of finding the edges of an image. How do I get a tensor out of that? Well, it might take my 3 by 3 block. To get an edge would mean that on one side I was one color, and on the other side I'm a different color, or black and white, let's say. That would be where I'm hitting an edge. I was white and then I became black. So that would be an edge. So how can I measure this? Well, I might go ahead and take my 3 by 3 grid and say, well, let's see, if I was to add this to that, did it come out as 0? If it was, then these two are kind of neighbors that are the same color. So if I do this along here, then what I'm choosing as a preference is edges that sort of are horizontal. Because they're saying that, look, the only place you should get a hit is if you come to a barrier where all of a sudden the above colors are different than the below colors, then I should get some numbers showing up. But any place that the above and below are the same, they should average out to 0. So this is detecting this thing here. But what's really happened is I've taken my entire picture and taken all 3 by 3 submatrices and made one long extruded list that's 640 by 480 long and 3 by 3 on the side. This long tube, I just dot product with that matrix all the way through. And then I add up all those dot products and get a long vector. It's a new image. And the image will be the effect of convolving this image with that matrix to get that. And what we see is it did a pretty good job of detecting the tops and bottom edges. Change the sides, this to that. I suspect one of us is wrong. I think the negatives are on this one. That's why you're seeing the back side of these here. But maybe I have to see. But you're seeing more of the horizontal side than when you did the vertical ones here. And then maybe you try to sort of say, well, I want all the edges. I want to sharpen my image. I could have sort of add up everybody to 0, but emphasize that you be close to the middle. That like on all sides you're a boundary, right? That shows up the whole shape in some sense. Okay, now all I'm trying to do is generate data for you. This is metadata from an image that I just apply this type of tensor contraction to get a bunch of new data that I can then feed to my machine learner to say, can you tell me why there is a bicycle in this picture? And it says, well, I found a circle because it hit on this vector. So I'm not doing the machine learning side of things, but I'm giving the metadata that then you can hand to the machine learner to then go learn. Another place that you see tensors built in life. Nevertheless, regardless of all the fancy examples that people have, and there are zillions, just Google this, this is by far the most important, is to just multiply matrices. And in here I'm going to multiply a matrix with a larger dimensional tensor. But what I'm doing is I'm taking the entire 3-dimensional tensor that I have a vector here, I slice it up, multiply matrices as usual, and then glue them back together. That's my giant tensor contraction. And there's very nice, lovely formulas that are purely mathematics. You don't have to see a picture at all that show that all this stuff is well defined, but they all fit under the same category of slam some numbers into your grid and add them up in some axis. And there's lots of flavors, including our logo. You can do it rows, columns, all 3, 2 of them. All right, so now we're going to change gears. Are there any questions here? Okay. I'm only going to give the surface of this one. Some of this I'm going to come back to in the next talk, so we'll see what we get to today. But we have now established that the context is these tensor spaces, so now we're going to act on them. And we want to try to take the metaphors from days past to try to get something here. And this is actually not a conventional take. In fact, it has new theorems at the end of this. But But if I was to start out with a linear algebra class trying to explain what is an eigenvector, I could just tell them an eigenvector is this vector that's stretched by a constant. But they would have no reason to believe that existed. And they'd just sort of say, well, he's the teacher, so it must be important. And this magical determinant is somehow going to give it to me, and I don't know what that's for. But if I was really trying to explore it with them, as in, how could you have discovered this tool too? I'd tell them something like this. Take your vector, take your operator, hit it, and see where it goes. It went somewhere else. Hit it again, see where it goes. And you get some dynamics. But the dynamics are bounded, because after all, we have some finite dimensional vector space, in this case 3. And you're hitting it with this matrix over and over and over. You're going to get an infinite sequence in a finite dimensional space. There will be a linear relation. Pretty quickly, in fact. And if you write down what that linear relation is, then you'll realize that you're actually hiding a polynomial. And that polynomial is trying to annihilate your matrix, or your vector. And that begins the whole story. This is what's known as the annihilator, or the minimal polynomial. And the roots of this are the eigenvalues, and then you can look at multiplicities and build something like the characteristic. And it's a very constructive way to build this. This is what you'd build in a program. But this is somehow not extended to the world of tensors as often as you might think. Maybe ever. But I recommend you do it, and here's why. Let's take a tensor now. Let's just take a simple 2 tensor, like just a matrix. But let's take 2 operators now. Let's act on the rows, let's act on the columns. And let's trace the same idea out. And you can do it. If you hit it on this side, it takes me to here. And if you look carefully at this matrix, you realize, oh, that's just picking off what? Top row. So once you've picked the top row, you just keep picking it, and you don't see anything new. So you write down the relation, x squared minus x. Right? You see that the polynomial x squared minus x is relevant to your story. And with y, I also picked a friendly matrix. This just picks the second column and then just keeps picking it over and over again. I get a y squared minus y. So that's not that exciting, because you could have explored that on just the vector space of R2 and R3 separately. Why the tensor? There's one that's new. See, if I follow x and then y, which is actually the same as y and then x, that's because of associativity of matrix multiplication. But if I follow that, what happens? I get a new unexpected relation involving both the x and y. And I guarantee that this is not obvious, because who here multiplies a 2 by 2 matrix with a 3 by 3 matrix? So you would not think of x times y vanishing if all I gave you was these 2 matrices. That they're not even compatible. So this is speaking about the tensor. And it's creating not just one polynomial, as in the previous linear algebra story, but now 3. In fact, maybe it creates even more. If you want, you can scroll down and see how you can do this yourself in a typical computer algebra system, how to make these. It's not, you can imagine your own, but there's already code here, so you can cut and paste it. Let's see a different tensor. So the only difference, if you look carefully, is, oh, actually I changed the operators, not the tensor in this case. So I'm going to use 1 minus x and 1 minus y just to say, same tensor, but explore with a different operator, what happens? Well, let's think before we do this. With linear algebra, what would happen if I changed to a different vector? Maybe nothing. Maybe I get the same relationship. But if I was unlucky and I picked the 0 vector, you'd definitely see something different, right? Because 0 would just stay at 0. And if I picked an eigenvector, you would only see it stretched by the eigenvalues. So it is possible for the for the polynomials to change by which vector you picked. So likewise, if I go look at this and I'm operating with these things here, I'll see if you trace this out and you trust my arithmetic. This did not go to 0. I don't have that extra xy in this one. So the change of operators with the same tensor can give you different answers. And likewise, if I change the tensor and keep the original operators, this is a different tensor, that's not 0. Look what survived. And in fact, you could start to sort of fathom why this is correct. The 2 operators I picked, it said pick the first row and the second column. And because that was 0, that allowed this one to hit on that weird relation that otherwise it wouldn't have hit on. But that's a property we might want to explore. We might want to understand, where are the zeros in my matrix? These are things called singularities. Where are the zero divisors in my product? If I can find those things, if I can explore them, I'm going to build a theory around them, I might make strategies that I can go search for them or prove some difficulty results if that's what you're interested in. It's an interesting way to see it, at least from my perspective. So what's actually happened here? Well, I took an A by B matrix, I took an A by A matrix, and a B by B matrix, and I hit a polynomial action. Because I said, well, I can act on the rows or by the columns by some powers independent and some coefficients. And as long as I treat that as sort of pulling out this polynomial times t, then I can ask the question, what are the polynomials that delete t, that annihilate t? And this is a classic algebra phrase for something we call an annihilator in general. You have a thing, a ring acting on a module. If it deletes it, that's the annihilator of this module. But unlike the classical linear algebra story, it's no longer k of x, it's k of xy, because the valence here is what? Our tensor is a what tensor? 2. So there's two variables because it's a 2 tensor. We're acting with two operators. That's why we have, instead of k of x, we have k of x and a y. If you're interested in wildness and tameness, scroll down. What's really going on here? Here's another interpretation of it. What I'm really interested in is every operator on the tensor space, every single one, because I don't know which ones are important yet. Well, I mean, it's an A by B matrix. That's just some AB dimensional vector space. So all the operators is all AB by AB matrices. It's a gigantic set. How do I study that and keep track of the rows and the columns? That's the key thing. It's one thing to say, oh, it's just a big vector space. Well, then you don't care about it being a tensor. So if I care about the frame of the tensor, the rows and the columns or the depths, whatever I have, then I have to keep that in track. And it's a little exercise. You can scroll down and see a proof if you like, but I can always partition my matrices into boxes that are A by A or B by B, and then factor that out into what's called the Kronecker product of these two things. More generally, if you have valence L, then I can take all those vector spaces and glue them together into one giant vector space and take all their endomorphisms. And I claim that if you pick an operator out of there, it'll always be representable by a polynomial like this. So let's see that a slightly more slowed down version of it. So here's the classic fact we started with. This is the linear algebra fact set in sort of different notation. If I take a single matrix, there's some polynomial behind it. And the idea is that I take my single square matrix and I have x hit it. So x to the 0 is where 1 goes. X squared is where omega squared goes. That assignment is the classical way to get a PID, a principal ideal domain, assigned to the original matrix. But then you do this in inductive ways. For all the variables, you put one of those PID standard representations, and then you just take their tensor products all the way through. Well, that's not quite the same as the multilinear spaces. Well, here's that little exercise. I was saying if you did this with Homs, you'd die. I tried this one with Homs and died. I did it without Homs and it was totally trivial. You just divide and move things around, and sure enough, these are the same space. And then you can put it together, and you see that at the end of the day, you glue all of these together, you get a map from here to there. So all multi-operators turn out to be a map like this. If you have a list of operators acting on a tensor space, then you really just have a representation of polynomials in that many variables into your tensor space, into the operators on your tensor space. And then you have immediately the notion of an annihilator, and this annihilator can be computed. What does that even mean? Well, I'm not going to go into the theory of Grosvenor bases except to tell you that if you're dealing with ideals in a ring, you need some tool to work with them. And you need to be able to tell, are you in this ideal or not? And Grosvenor bases is a nice set of generators that lets you quickly check if something's in there. And almost no theorem I know of that uses Grosvenor bases gets to say polynomial time. And I'm going to say it. And the reason is that it's polynomial in the input. And here, what I have done that's different than, say, standard Grosvenor bases things here, is that I'm only interested in the number of variables matching the valence. It has nothing to do with the dimension of the vector space. You could have a 900 by 10,000 matrix, and I'd still use 2 variables. And Grosvenor basis isn't actually hard with a fixed number of variables. It's hard when you have a lot of variables. There's particular bounds. But if I have 2, 3 bilinear maps, trilinear maps, that's a bounded number of variables, and so I can do my Grosvenor basis computations, and you can just try these. The dimensions don't matter. The dimensions of the axes don't matter. That's a big difference to sort of standard things. So that's why I'm not hitting NP completeness in this side of the story. So this has a little bit more range in terms of applications. Of course, there's a downside, right? If you're solving an NP hard problem, then the benefit is you probably learn a lot more interesting information than you will from this tool, right? Any tool that's easier to compute is therefore more useful in that sense, but it tells you less. So I'm not trying to say one's better than another, it's just different. This one will compute very quickly on large dimensions, but it won't introspect as much. Here's another example, just to sort of see this in 3 dimensions, and to see different types of operations, or sorry, different types of relations show up. Here I'm going to just multiply by these 3 matrices, and if I take this here, the convention here is that this is really a 3 tensor, and I have 2 vectors. One of them is E1 and one of them is E2, but I called them 1 and x, just because it's easier to type, and because I know where this example is coming from. If you know what this is C adjoin x mod x squared. That's just, that doesn't matter, but nevertheless, that's where the notation comes from. So this is a 3 tensor. It's a 2 by 2 by 2, and I'm acting in all 3 sides, and it becomes, oh look, these are the same, and these are the same. So I get these kinds of mixed relations. And those would not be sensible in general. It's not just the axis that's telling me that. Here's a different example of a 3 tensor. Trying to illustrate again that I have 2 basis vectors. One of them is saying in the 3 direction I have a 1 and a 0, and then a 0 and a 1, but I'm going to write them as x and y. Okay, I just can't draw that 3-dimensional picture and stare at it really well. So I'll write it like this, and I claim that if you took these operators, they would satisfy some weird rules. And I claim that, in fact, they'll satisfy, say, x2 minus x1. You have to go through it. I'll let you do the exercise. More generally, if I have like a whole row like that, a bunch of things, so it's kind of each vector is a different thing going down there, and I multiply by any matrix, then you'll notice you get a really crazy relationship here. So if I multiply by, and I wonder if I can write on the slide, hope that's going to mess things up. Well, I won't do it. I'll just tell you what I'm doing. Is that I'm multiplying, in this one I have the identity and then A as a block matrix. So 1 by 1 and then an A matrix. So then that's striped, actually which way? So in this one it was on this side, it was acting on the columns. 1 and then A transpose came through and became that. From here to there it was 1 and A multiplying there. And then from here to there it was multiplying A on all the U's. And I claim if you check this out and you do the Grosvenor basis, you'll find this relationship, this little quadratic here. What am I trying to demonstrate? They're not just linear things that come out. You can have, well actually I don't know what you can have. It's a question I have. What can actually happen here? How generic are these ideals? Is it every ideal? Well certainly I can get things like, I've gotten all parabolic equations, all hyperbolic. I have not yet gotten elliptic curves. But I suspect it's doable. And if I did get elliptic curves, especially of high genus, then I would know this clearly is in the world of algebraic geometry. Like there is a story here that I don't understand, and that's based on how many examples I've bothered to compute. You know, like there's a lot out there. I would love to see people just explore. This is, you can just simply just guess, or take some intuition of experiences you have and see how crazy are these operators. I suspect the answer is they're crazy. But maybe I'm wrong. Maybe they're a very special subset. As you find them, I'm happy to hear about them. And if you don't put your name on it, then I'll put mine on it. So make sure to put your name on it when you send the email.
I have a question.
Yeah.
Can you clarify what you mean by getting a parabolic, getting a hyperbolic?
Well, so y equals x squared. Can I find an A by B matrix and operators x and y such that y minus x squared is an element in the Grosvenor basis of the annihilator? That would mean a quadratic. That would be a parabolic. A parabola, I mean, and a hyperbola would be, an ellipse would be an x squared plus y squared equals 1, and things like that. And I don't know. I don't know what I can get. But it feels like if we could finally understand what can occur, we would know what toolbox of mathematics is the right one for it. All right, well, let's call these things traits. If I take the Grosvenor basis as just the universally definable thing, it's unique up to the ordering, we can have great discussions on what the right thing is there. But anything that shows up here is going to be interesting to study on its own right, so let's study them. And if you go to the books that exist on polynomials, you already have a good guide for what you should do. You should look at the primary decomposition. If you know what that is, then you're with me, and if not, you can go down and say, oh, it looks like just factoring a polynomial. Yeah, it's just that, but on steroids. These are ideals. Whatever x and y's and z's can do is very murky. You can get examples where things intersect in strange ways, and you have primes inside of primes that skip each other. Oh, it's a wonderful zoo. I'm not the one to tell you about it. But that's a great place to start, and it does tell you a lot of the features that are interesting right off the bat. But one of the things that happens is that by having the axes, the very action that I can take x and just act on the rows, means I'm going to hit the minimum polynomial of x. And just by acting on the columns, I'm going to hit the same, the annihilating polynomial of y. So at some point, those force those eigenvalues to show up, which means that you get these zero-dimensional curves, if you know what that means. You just get points in space instead of nice curves. But you can see the evidence, like the xy or x squared equals y, those kinds of things. So they're points in which you know there's a curve going through them, but the curve isn't part of your data. So I'd like to see the curve rather than just some points on the curve somewhere, right? So how do I hone in and look at the entire curve of these operators rather than just 2 or 3 points for any individual operator? Well, the answer is you take more operators. Just involve more operators. Why? Because each operator pair is telling me this point and this point on the curve, but another set will move it to another place on the curve, and eventually I'll see the whole ellipse if I look at all the operators that ran through that trait. And this is just saying that I can take a set of tensors and a set of polynomials, and I can look for all the operators that share that trait. Build up the biggest set of all of them that have that. Let's just give a quick example of it. This is a standard alternating form, I minus I. And here's a trait that I'd like to explore. This is just what? A hyperbola, right? This is x times y equals 1. This is y equals 1 over x. So I have the curve this way and the curve that way. If I pick a single operator, it'll just be a point somewhere on that hyperbola. And I have no right to talk about hyperbolas then. It's just a point on the hyperbola. How do I talk about the entire hyperbola? Well, I look at all the operators that satisfy this, and actually, wait a minute, I know that's an important thing. Because that's the group of, well, sometimes they're called conformal symplectic maps, because I didn't have scalars removed. Okay, but you can make a unit version of this if you want. So this is what happens over and over again with all the interesting traits that you can see. Well, I don't know what interesting is, but with many of the interesting traits, when you write down what are the operators that satisfy that trait, you say, of course, that's the group of isometries. That's the set of derivations. That's the Jordan algebra Hermitian elements. It's a thing that we already are studying, but with a different track to it. And so, okay, we can go backwards. We can take the operators that we're interested in studying, because we've seen that we're seeing operators we know about. Let's see if they, in fact, give us good ideals. Take operators that you know are interesting, take tensors that you're trying to study, smash them together, and get the traits that they have in common, just reversing that process. Or maybe you want to take the metaphor of eigenvectors, right? What good is an eigenvalue if you don't have a vector to stretch it by, right? I mean, that's the whole point. So I could take an existing trait that's interesting to me, I could take a set of operators that's interesting to me, and I could say, give me all of the tensors with these two. And that's the metaphor of eigenvectors, okay? And that's what this T set is. And all of these are definable. The only one that's not computable is the Z set here. This set in general requires a quadratic number of variables, and any Grosvenor, it's a scheme, whatever that is, so it's got a name, it's a type of set of operators, and computing these might be hard. But the T sets and the I sets are all doable. Let's put this together. This is with Udia first, who was photographed on the first page, and Josh Maglione. Udia is happily not able to make it. He's getting married this week. Congratulations. Please return to us. So here's the correspondence there. I mean, it's not that deep, but it really feeds into how you think about these things. If I give you a field and I think of extensions, then I can think of the automorphisms of the roots as giving me a group. And so what you have is the inclusion this way gets flipped to an inclusion over that way. That's what's called a Galois connection or a Galois correspondence. This is one of those, but with 3 parts. If I give you a tensor space or a tensor or a set of tensors, and I give you some traits, some polynomials that I'm interested in studying, then there is already a well-defined perfect set of operators for that pair. Likewise, if I have some operators, some isometries that I'm interested in studying better, and I have some tensors, I can find out what traits they have in common. Why are these special operators happening on these tensor spaces? Oh, they actually share this extra trait in that ideal. So I can start to explore what's special about this combination, and so forth. There's this trinary, I don't know what to call it, ternary, ternary Galois connection. And I'm going to go through some of the details, but not that many of them. But here's the big takeaway from this approach, the summary facts. Most of algebraic geometry is very, very deep, difficult mathematics. It just is. People have been exploring it under revisions for at least a century. But there are at least 3 categories where you can make some progress. If you have ideals generated by linear equations, well, then we're gold. That's linear algebra. We've done really good with that over the last century. Another trait that's nice is monomials. If I just have something like x squared or x times y, they don't add anything else to it, just powers of the x's. That's a nice enough trait to be able to do some of the calculations. For example, you can do Grosvenor bases very efficiently in that case. Doesn't matter how many variables, it's efficient. And then there's one final family, which is when you take 2 monomials, you add them together or subtract them, they call them binomials, and that too has a nice Grosvenor bases theory, but by no means is it easy. This is Harris and, I'm forgetting who did the main work on this, but this was a deep series of papers that really proved you can do this. Strumfels is really famous for a lot of his work in this area too. Beyond that, it's known to be what's technically known as wild. You just cannot succeed at classifying. It will get worse. But in these 3, these are the ones that we've concentrated on, we can tell you what's going on. So these are what algebraic geometry tells us you can survive here, so that's the ones we're going to look at for traits. So linear traits correspond to derivations. So this is the first one. So let's think about how you would approach this. If you're an algebraic geometer, or anybody really, you might think of this approach even independently. You could think of lines, you can think of planes, and if you're in a big enough space, eventually you're going to think of the largest space, which is a hyperplane. And if you're in geometry, it's no different. You can think of a hypersurface, the largest thing. And if I'm interested in the traits that have the most influence on tensors, they're going to be the traits that have the largest possible dimension, because that's the way that they'll have the most hits, right? The larger the dimension, the more likely my operator hits one of these traits. So these are the most influential traits, are the ones of the highest possible dimension, the hypersurfaces. And that's not that easy to get your hands on, but there is a small special case. If you look at things projectively, you assume everybody's going to go through 0, then there is such a notion as a generic hypersurface. And it's not really clever. It's just add up all the monomials with non-zero coefficients. You know, if you were to perturb something that had non-zero coefficients, chances are it's not going to become 0 at that coefficient very likely, right? So it's generic. You can move it around. Its neighbors look the same. If you do this, you can start to sort of think of a strategy to study the highest dimensional surfaces in generic terms at least. Maybe they'll have exceptional cases, but generically you can see what's going on. And let's do this for linear because we can actually do linear algebra. If you do that, I'm going to pick one specific generic homogeneous polynomial. And I did one small thing other than the obvious thing, right? Just take ones. But I put 0 at negative, and that's because it's always one of these contravariant variables. It's at the end of the function, it's codomain, and those classic things you have to swap. So let's put a minus there, it keeps track of it. If you write down what satisfaction means here, what does it mean to annihilate with this trait, it turns out to be a well-known equation. Like I said, these are just experiences showing us that the things that show up are the ones you thought should have shown up. Derivations. If I just had 2 variables, this would be saying that delta of a product is delta times the product, product times the delta. It's just the Leibniz rule. And this is generic. And so what this means is that you can actually prove theorems like this. Any trait that's linear over a big enough field, so for small fields like 2 and 3 you might have some trouble, but if you make a big enough field, then any linear trait embeds into derivations. Any linear trait. Now, that may not seem like anything. I've just introduced a bunch of words, so you can say whatever I want about them and you should just believe them. But let me say something that I think most of us know. When you take a tensor product with rings in the classic textbook, what kind of rings are they? Associative? Lee? Jordan? Tensor products are introduced with associative algebras. But when you start talking about derivatives and Leibniz rules, what class of algebras do you study? Lee. This harmless looking set of symbols is saying something's wrong. Whitney said tensor with rings, associative rings. And we just proved that actually the hypersurfaces generically have Lie structure, not ring structure. Who's right? Well, there's a way to ask that question. You could say, let's go ahead and not be biased to who's right. Let's say that you can put any product you want on these things. You could put Lie by putting 1 and a -1. You could put associative by putting 1 and a 0. You could put the op by putting 0 and a 1. You could put Jordan by putting 1 and 1. You could put some crazy mixed up thing in there. These are what are called weakly associative products, Jacobson's term. So let's just say that, and you can do it in any coordinate you want. Just put whatever one you want. You know, like on the x-axis you do associative, on the y you do Jordan. Pick whatever one you want. And I have to say, this is one of those moments when you think, how did this get through? It's a fluke. If you want to make an associative product on the set of operators that have linear constraints, it'll work exactly on 2 components. 2. It'll always work with Lie, but it'll only be possibly associative in 2 components. How many components do we have in this product? And once you realize that, you start to realize, why did we ever do it this way? Look, if you try to take Whitney's definition too seriously, you immediately have to retreat. Take a tensor product of 2 vector spaces over a ring in the middle, and then change your mind to swap it. Somebody has to be opt. It's on the wrong side, right? This is acting on this side and on that side, and now they're on the outside. What do you put there? It has nothing to do with A. It's a totally different ring. You can't write the associative or the commutative law. It's only if you put something like the scalars, and that's because it's commutative, and so therefore it acts on the left and the right at the same time, and so you didn't really have a side. So it doesn't work. That commutativity is just not true, and so the retreat is to go down to the integers or to the field. But if it was a Lie algebra, Lie brackets are skew commutative. They pick up a minus sign, but you can make that act on the left or the right. What about associative laws? Same problem. If you want to move the parentheses, you have to also move the operators. And if you can't move the operators, then you just get rid of the operators and put a pointless operator there, like the integers. But if it was a Lie algebra, no, it doesn't matter. It can act on all 3 at the same time. What if you had more than 3? You had 700. Well, a binary product between 700 things has 699 places to put operators. But how many subsets of these operators are there? 2 to the 700. So you're missing almost all the other operators. V3 never gets to talk to V1 through these tensor products. Never. If you don't put it next to it, it's not allowed to talk about V1. It doesn't see anything at the tail or the end. And then you're not using your operators. You've artificially limited it by thinking of it as a binary product. You said, I only want to see the neighbor. I don't want to see the whole space. And once you think about it, you realize this is so unnatural. But if you do it with a Lie algebra, you can act on as many things with all the operators that you want. So this is the summary of these. If you define a tensor product not as a Whitney tensor product, but just in this universal guided by the operators, guided by the traits, guided by generic choices, not trying to bias it, but just say what actually happens when I put linear constraints, I always get a Lie algebra. And that Lie algebra can act on as many spaces as I want. And the result will be that it works. It solves all those Whitney problems. If I have a message to take home from this, it's that I think, cautious to say this, I think that the Whitney tensor product is the wrong tensor product. Careful saying that because I know I'm fighting 80 years of people telling me I'm wrong. I can only point to what the math is saying here. Let me end with just a couple slides of stuff. Monomials, much more interesting polynomial than linear. All I want to say about them is they point to singularities. We already saw that when we had the x and y show up, it was because we got that zero matrix in the bottom. And if you really think out through, it's actually not that deep of an idea, but somehow you just have to stop thinking about it in a different way. But if you think about it, it's all the operators that are localized, that they go to the same place as a singularity, that's exactly when you get a monomial. But let me show that to you rather than give you symbols. See, if you have monomials, then the ring you're getting, this quotient by these ideals, is what's known as a Stanley-Reisner ring. You don't have to know what that is, but what you can tell is that that means there's combinatorics. That means that you have a simplicial complex somewhere. And if you take a 3 by 3 box and you start putting zeros in, the first thing you can do is no zeros at all. Well, let's call that the filled-in simplex. Let's take a 0 out of this corner, non-zeros all around it. Poke a hole in the face. Let's take and put a whole slog of zeros in one column, so it's got like an L shape of non-zeros. That's taking away an edge. And if you keep doing this and removing non-zero parts, you start to see a scaffold of how to do this combinatorially. And it lets you now think about singularities in a higher dimension than I can actually visualize, because I can draw a simplicial complex that's very complicated to talk about a 24-dimensional space having a singularity. What kind of singularity? How did it get there? Is it isolated? Is it surrounded by non-zeros? Does it have paths to it that are zero? And these are invariants of the algebra. Any basis change is going to apply to the same thing. All of a sudden you have structures you can start to permute. If I have singularities of one class, they can only go to singularities of that same class. And now I have structures that tell me about isomorphism invariance, the structure of my data. It's just a thing you can do. And this one is just a tease for the last talk that I'll be giving this week. If you put binomials in, then you can study the groups. Okay? And the answer is going to be that any time that you have group structure on here, then it was because there were binomials in the background. Okay? Now, I'm not going to show you how until the next week, but because Peter told me that he's going to not do this one, I'll show you the last application of knowing this. Here's a classic question that shows up in engineering circles a lot. I give you a bunch of matrices. They can all be square if you like, but make them rectangular in this case. And I ask, can you simultaneously diagonalize them? Block diagonalize. I don't have to be one by ones, but something down the diagonal. If you could do this, you can start to do things like clustering algorithms. You can find the direction of your data. It simplifies. It's certainly more sparse. I'm not really sure what all the uses are. I came to this problem because I was interested in something called central products of P groups. Nobody in the room cares about that, but okay. Two of us care about that. But the point is, it's an esoteric area. But the point I think is great about tensors is how, once you really understand what the questions are, they find fundamental questions in everyone's research. So whether I cared about chat room problems and clustering and dimension reductions and things that engineers might care about, no, I cared about a P-group thing, but it's the same question. So let me show you why this is hard. If I was to take a single matrix and I wanted to make something orthogonal, I'd take any vector, and Graham-Schmidt would tell me how to move any other vector to make it perpendicular. It's greedy. Pick any vector, a non-zero vector, and another one, it's not going to be linearly dependent with high probability, and then Graham-Schmidt is perpendicular. Do this in as many dimensions as you want. Try two matrices at the same time. I give you two matrices, two bilinear forms, and I say try to make it perpendicular with respect to both at the same time. This little video is to demonstrate that. What's happening is that the grid here is a hyperbola, which is one matrix view of perpendicular. And everything that the red and blue are doing as they're moving is perpendicular with respect to the hyperbolic basis. So these are perpendicular with respect to that. But that does not look perpendicular to the grid, does it? So my two matrices are the standard Euclidean, where that's perpendicular, all of those. But these are not perpendicular. And so what you find is that you can make them simultaneously perpendicular, but only in one unique way. How greedy is that? You cannot pick one vector and then make it normal to the other one. You have to pick the right first vector. So this is the difference between taking a single matrix and block diagonalizing it and taking just two. No chance at doing this by random luck. You cannot pick a greedy thing and march. But I claim that the answer is already solved, not even by me, but by like 40 years of research in group theory. And it was because they were actually hiding these traits. If you write down what's happening for orthogonality, it turns out to be some natural traits. And people already worked out algorithms to find these traits without really even having that vocabulary. But now having it, we can expose that existing work within bizarre circles. Look, this one here is for the finite simple groups. If you don't know what that is, yeah, neither did an engineer, right? I mean, this is not, I don't even really understand the finite simple groups. This is not something that you should have to know about to try to block diagonalize the matrices. But it's something that's really functional. It's something called the medax. I believe, Alexander, you're going to speak on the medax. So you'll see what that actually is and how this might solve this problem. And if you don't see it, feel free to ask us. Here's a different kind of decomposition. What if you want to put things on these diagonals? You know where I found that one? A theorem on logic. Logic cared about this. There it is, just the right trait. Maybe you want to have symmetry. You want to have that, if you transpose it, it's the same. This is from Jordan algebras. Here's a more complicated one. This comes up in a chat room problem, and this was done recently. Once I sort of studied this, then I said, well, let's take some of the other traits and see what happens. And this was just the fun one to try, the derivations of the generic one. Sure enough, you can find these kinds of traits. I don't know if they're really useful, but it's at least teaching me how to think about decompositions in a different way. You can start to target the things you're interested in with something like a polynomial of some kind, go build a theory around that, then come back and build an algorithm to find it. I think that's the promise, is to sort of start building new tools. Not that the old tools are bad, but just to add to the toolbox. All right, throughout the week, please come up with your questions, but I'll take any you have now.
Thanks, James, first.
I mean,
Is there a homology theory for tensors?
well, I'll tell you this. In the next talk that I'm giving, I'll describe that there are enough projectives. That's as far as I've taken it, but there are projective resolutions, so there is a homology. I don't know anything about it. And I can say, actually, I'll add one thing. The categories of tensors, whatever they are, I can prove they're not module categories. So they're not just recovering a known category in a different language. It's a different category. It might be somebody else's known category, but it's not any that's just standard modules. So whatever homology theory you're getting is perhaps different than the module theory. Anyway, I'm happy to have all of us go make sure we eat enough calories to make it through the rest of the day. So Josh, should we stop this somehow?
Thank James again for